This video will be the first in a 5-part mini-series about the science of climate change. And this video in particular, we will introduce the topic of climate science and climate change, and we will discuss some of the important concepts and definitions that are needed for understanding the science of climate change. And we will look at some of the data indicating both that the climate is in fact changing and that human activity is contributing to the change of the climate. And we will examine a syllogism that I've put together that, if it's sound, makes the conclusion that human activity contributes to climate change undeniable. So to deny climate change, the conclusion here would require refuting at least one of the premises of this syllogism. So first, let's talk about a few terms that we need to know. So the first one, which is very important for climate science, is what's called radiative forcing. So this is essentially just the change in the energy balance such that the change in the difference between the energy coming in and the energy going out is not equal to zero, meaning that either more energy is coming in than is going out, or more energy is going out than is coming in. And so we tend to want to know what the contribution some parameter has on radiative forcing. So you'll hear people talk about, we want to know what the radiative forcing of carbon dioxide is, for instance. And what that is asking is, if we increase the carbon dioxide by a certain amount, how much is this going to change from being equal to zero? Where this would be equal to zero if there was no climate change. The next thing we want to think about is what's called the temperature anomaly. So the temperature anomaly is the difference in temperature at some time point t sub 1 compared to the temperature at some reference time t sub 0. Usually the reference is an average of temperatures over some time period, for instance like a decade. So what the temperature anomaly is telling us essentially is the difference between the actual temperature and the temperature predicted if there had not been any climate change since the reference temperature was taken. So it's essentially just telling us how much the temperature has actually changed compared to some reference point in time. Another one, this one won't be as important to us in this video, but it will be in the coming videos, is what's called the solar constant. So this is just the power in watts that will hit a square meter of space at some distance from the sun. So when we think about, for the Earth, that's 1.50 times 10 to the 11 meters from the sun. The solar constant, so pretty much anything in that distance from the sun, which would include the Earth, will on average be hit with 1361 watts per square meter. And so that has to do with the energy coming in. So that would be part of our E sub in right here. And the E sub out is what's called the outgoing long wave radiation, or OLR. So this is the infrared radiation that is actually leaving the Earth. So that would be the energy out. And so we can see that if we have no climate change occurring, then the energy coming in and the energy going out should be equal to each other, and so subtracting them should be equal to zero. Whereas if we have radiative forcing, then this will be not equal to zero. So just to drill down into a couple of these in a little bit more detail, the radiative forcing, as I said, is essentially just solving this equation right here, where it's just the energy coming into the Earth minus the energy leaving the Earth will be equal to the radiative forcing here, where the radiative forcing will have units of watts per square meter. And we can see if the radiative forcing is equal to zero, then the energy is in balance. The same amount of energy is coming in as is going out. Whereas if the radiative forcing is greater than zero, so if it's positive, then that means more energy is coming in than is going out, because it would mean that this E sub in is bigger than this E sub out here. And this will lead to warming, because we are gaining more energy than we are losing. But if the radiative forcing is less than zero, so if it's negative, then more energy is going out, because this E sub out would be bigger than this E sub in, and this would lead to cooling, because then we would be losing more energy than we are actually gaining. And so this is what the radiative forcing for these different greenhouse gases actually looks like. And so we can see the radiative forcing for each one is increasing as we go through time. So over here, this is the radiative forcing in this units of watts per square meter. And so we can see with the carbon dioxide, which is this lower one here, that's kind of the maroon color, we can see that this has gone from this 1 watt per square meter up to something like maybe 2.3 watts per square meter. And that's just from the carbon dioxide. We can also see this for a few of the other greenhouse gases up here. And we can see just from the greenhouse gases all combined together, we're getting about 3.5 watts per square meter of radiative forcing. So then the temperature anomaly, which is an important concept to understand because it's used a lot in climate change science. So if we have something that looks like this, where we have our T reference, so that's our reference temperature, and so this is the temperature from January 1 right here to December 31 of this year. So this is the temperature of that entire year. So that is our reference temperature. Then we want to take the temperatures at some later time, and we can plot them like this. What we see is that they are higher for all of this until we get to here. Then the temperatures for this year are actually lower than for our reference temperature. And I'm doing that just to show that we can have a negative temperature anomaly. And so then if we want to get the temperature anomaly for these three dates right here, so for April 1, July 15, and November 1, what we do, we just subtract the reference temperature from the new temperature. So this would be 2 degrees temperature anomaly for April 1. Then for July 15, it would be 6 degrees. Then for November 1, we see it would be negative 2 degrees Celsius. And so if we wanted to then plot that temperature anomaly, we could do it like this, where we can see at the April 1, we're at about plus 2 degrees Celsius, the July 15 at about plus 6. Then we can see over at the November 1, we're now at negative 2, so that's below this 0 degrees right here. And we can look at this for some real data right here. So this is the Earth's average temperature for these years right here. We can see up at the top, this black one is for 2024, this red one is for 2023, this orange one right here is for 2022, and we can see that in general the temperatures over time have increased, and that's all throughout the year. So this is plotted over the year, and so that's why it bumps up in the middle right here, because this is summer in the northern hemisphere, so it's warmer. But then if we wanted to take the temperature anomaly, so we want to subtract a reference temperature off from each of these temperatures for each year, then we would get something that looks like this, where we can see right here is our 0 temperature, which would mean that there is no change in temperature from the reference temperature. Anything below that means that it's colder than the reference temperature. Then up here means that it's warmer than the reference temperature. And we can see that the 2022, 2023, and 2024 are all warmer than the reference temperature. In fact, you can see that as we get further and further along in the years, that the average temperature anomaly just keeps increasing as we get closer and closer to the current year. So that, of course, is one of the bits of evidence for the fact that the global average temperature is in fact increasing. So the next thing I want to do is talk about this syllogism I've put together, but first a few definitions before we get to that. So the first definition that we'll need for this is what's called the human activity. So this is just all the activities humans engage in that requires energy. So pretty much everything that humans do. Then we have what's called the greenhouse gas. The definition of this is just a gas such that if its concentration in the atmosphere increases, then the energy coming into the planet will be greater than the energy leaving the planet. In other words, our E in minus E out would be greater than 0 until such time as the planet warms up enough for the amount of energy leaving the planet to be equal to the amount of energy coming into the planet. So it wants to reestablish this homeostasis here. And remember, this is our definition of radiative forcing. And to look at this a little bit more detail, what we're talking about here is if we have some piece of metal here, this gray piece of metal, it's radiating like something that we call a black body. And so there is going to be energy coming into it just because of the ambient air temperature. So the energy in is equal to the energy coming in from the air. The energy out is equal to the energy leaving by infrared. That's what the IR means. And when we are at this homeostatic point, then E in is equal to E out. But then let's say we apply some heat to this piece of metal. So now the E in is equal to the E air like we had before, but now we're also increasing the heat going in by this fire right here. So we've lit this fire here. So the E in now has this E fire coming in right here. So we can see the heat coming in goes up like this. So this is the change in our energy in over time right there. And we would then end up having the E out start increasing as well, but we can see that that is actually going to lag behind the E in. And so at this point, E in is greater than E out. We see that as we continue heating it, the E out is going to start increasing. So now the E of the infrared starts actually increasing. So we're starting to lose more heat, but at this point at T2, we are still gaining more heat than we're losing. So that means this piece of metal is still heating up. So E in is greater than E out at this point. But at some point, the E out is going to catch up to the E in, and so we are going to get back to the point where E in is equal to E out. So the amount of energy coming in is equal to the amount of energy leaving the metal. And so that is when the temperature will not increase anymore. So for instance, that's why when you start heating up a pan, it doesn't just heat up to infinite temperature. It heats up to the point where it's going to be losing heat at the same rate that it's gaining heat from your stove. And so at this point, again, the rate of energy in is equal to the rate of energy out, but now this has to be at a higher temperature. The temperature that it is doesn't matter as much as the rate at which energy is gained compared to the rate at which it is lost. And once we turn on this fire here, then the rate at which it is gained being equal to the rate at which the energy is lost is going to be at a higher temperature. So it has to heat up to a higher temperature in order for the energy lost to be equal to the energy gained. And so we've been talking about temperature here, and we obviously know that it's based on something to do with energy, but it's not just based on it. We actually have an equation for it here. So we know quantitatively how much the temperature depends on the energy. So the temperature is just the average amount of kinetic energy in a system, and it's related by this. So here is where we have energy by itself. Here is where temperature is by itself, and we can see that there is a direct relationship. As the energy goes up, the temperature is also going to go up. And the last definition we're going to use for our syllogism here is what's called the global average temperature. And so this is just calculated by combining the temperature measurements from thousands of locations across the globe, both on land and in the oceans, then averaging those temperatures. Since temperature is related to energy, as we see up in this third definition here, this can occur if the amount of energy in the planet increases. So essentially what this is saying is that because we know that temperature and energy are related this way, if the amount of energy coming into Earth is greater than the amount of energy leaving Earth, then that's going to lead to an increase in the temperature here. So now let's get to this syllogism that I've been teasing. So premise one here, if carbon dioxide emissions due to human activity during this time interval delta T increases the rate at which CO2 is added to the atmosphere above the rate at which CO2 is removed from the atmosphere during that same time interval delta T, then the amount of CO2 in the atmosphere will increase over delta T. And we'll go over a little bit more justification and explanation of each of these premises here in a minute, but this is my premise one for the syllogism that I've made. Premise 2 is very similar, but as we'll see, it is slightly different from premise 1. Now, premise 2 is if there is no mechanism to remove CO2 from the atmosphere sufficiently fast, then overall CO2 concentrations in the atmosphere will increase over this time interval delta T. Then premise 3, if CO2 is a greenhouse gas, as we defined it in the previous slide, then increased CO2 concentrations in the atmosphere will cause more energy to enter Earth's atmosphere than to leave it. So that is the radiative forcing that we were talking about. Premise 4, if more energy comes into Earth's atmosphere than what leaves it, and there is no other mechanism for mitigating the extra added energy, then excess energy will be added, leading to increased global average temperature over this time delta T. And this one here will be confirmed by modus ponens if P3 is confirmed and P6, which we haven't seen yet. So these four right here, I have them colored blue because these are the material conditionals. These are the hypotheticals here. But then comes the factual premises, which are the things that the science is actually going to try and determine. So the first ones of these, which is P5, is that human activity releases CO2 into the atmosphere. So again, this is something that you would actually have to go out and measure in the real world. The ones in blue here, like I said, are these sort of hypotheticals. So then P6, there is no other mechanism for mitigating the extra added energy. So that's going to go towards the modus ponens here on P4. And so we'll talk more about this one here in video 3. So we will not really be confirming P6 in this video. P5 will confirm a little bit more, but P6 we'll talk more about in video 3. Then P7, there is no mechanism to quickly remove all excess CO2 from the atmosphere. So this is a modus ponens on P2 up here, and this we'll talk about more in video 3 as well. Then P8, CO2 is a greenhouse gas. And so this would be modus ponens on P3 here. And we saw for P4 that we have to confirm both P3 and P6. And so if we can successfully defend these 4 right here in red, then these 4 here in blue will be confirmed as well through modus ponens, and that will support our conclusion. This one, again, we'll talk more about this in video 4. So we won't really confirm this one in this video so much, but we will talk about this in video 4. Like I said, if we can show that P5, P6, P7, and P8 are true, so that's what the science needs to show are true, then by definitions, these first 4 here will be confirmed, and then we will have supported our conclusion right here. So, like I said, these are the hypothetical ones right here, so let's justify these a little bit. So for the first one here, so we're saying that if the CO2 emissions due to human activity over this time interval increases, the rate at which the CO2 is added to the atmosphere above the rate at which it's removed during that same time, then the amount of CO2 in the atmosphere will increase over this time interval. So this can be justified by saying that, in general, if you start adding more stuff to something than it's being removed from it in some time interval, then it's trivially true that the stuff over that time interval will increase. So in other words, if the rate at which the CO2 is emitting is greater than the rate at which it is being captured, then what we would see is that the concentration of CO2 at T2 will be greater than the concentration of CO2 at T1. Then P2 here, if there is no mechanism to remove CO2 from the atmosphere sufficiently fast, then overall CO2 concentration in the atmosphere will increase over this delta T. And so this can be justified by saying that if you are removing some stuff from a thing more slowly than that stuff is being added over this time interval delta T, the net result will be an overall increase in that thing by some amount CO2 added. So in other words, if the emissions of CO2 is greater than the capture of CO2, then if we define excess CO2 as just the emission minus the capture, then we can say that the amount of CO2 added is just the added up amount of excess from time T1 to time T2, and that would be greater than 0. In other words, it would be non-negative, meaning that we are adding the CO2 to the atmosphere. So again, to me, this one just seems sort of trivially true. Then P3 here, so premise 3, if CO2 is a greenhouse gas, then increased CO2 concentrations in the atmosphere will cause more energy to enter the Earth's atmosphere than to leave it. And this is justified just by appealing to the definitions of greenhouse gas and global average temperature from the some definitions slide. So in order for this one not to be true, you would have to take issue with one of those definitions. Then premise 4 here, if more energy comes into the Earth's atmosphere than what leaves it, and there is no other mechanism for mitigating the extra added energy, then excess energy will be added, leading to increased global average temperature over delta T. So same as before, and using the definition of temperature from some definitions, we know that if more stuff is coming in than is going out during this time interval, then we will end up with more stuff accumulating. So for temperature, this looks like this. So if the energy coming in is greater than the energy going out, then if we define the excess energy as this difference in energy in minus energy out, then the energy added is just the amount of excess added up from time 1 to time 2, and this is greater than 0. Then if we say that the E added at time T2 is greater than the E added at time T1, then the temperature at time T2 will be greater than the temperature at time T1. That's just because from that definition of temperature, we know that energy is related to temperature. So if the energy at T2 is greater than the energy at T1, then the temperature at T2 would have to be greater than the temperature at T1. This is, of course, if there is no other mechanism for mitigating the extra added energy, which is what we will be talking about more in video 3. But again, this one seems pretty trivially true that if you were adding stuff to something faster than you're removing it, then you're going to end up with more of that something. And so, like I said, those are the hypothetical premises here. It's these 4 right here, P5, P6, P7, and P8, that the science is going to actually have to try to establish. And so that's what we are going to try to establish through this video and then the next 4 videos coming after this. So the first thing we want to do is try to establish that human activity is the thing that is putting carbon dioxide into the air. So this is a general formula for the combustion of a hydrocarbon. So this is our hydrocarbon right here. This is our oxygen. This is the CO2. This is the H2O. So we want to come up with the numbers that go into each of those for each different type of hydrocarbon. So if this is odd right here, this N, then this M will be 1. If this is even, then it's 2. So if we do this for octane, which is a major constituent in gasoline, it looks like this. So we end up for 2 moles of our octane, we make 16 moles of carbon dioxide. For another constituent of gasoline, which is heptane, it looks like this. So we're making 7 moles of carbon dioxide for each 1 mole of heptane. And each of these types of reactions for a hydrocarbon will look like this. But if we look at what is actually happening here when we burn the fossil fuel, it looks like this. So by weight, the combustion of gasoline, or as they call it in other countries, petrol, this releases 46.7 megajoules per kilogram. Here it is in a few other units, or by volume 33.6 megajoules per liter, and here it is in a few other units. So we are getting quite a bit of energy out of this hydrocarbon, which is of course why we use it in the first place, but it does actually generate CO2. So using 1 kilogram of CO2, which is a little bit more than 1/3 of a gallon of gasoline, we're going to make a little bit over 3 kilograms of CO2, or a little bit under half of a gallon of CO2. And what we find is that for every 1 gallon of gasoline we use, we're making about 1.18 gallons of CO2 gas. So every time we burn a gallon of gasoline, we're putting about 1.18 gallons of CO2 into the atmosphere. And in the US in 2024, the average American made about 14 tons of CO2 per person. That's going to be different in different countries. Most countries are quite a bit less than that, but for the United States, we made about 14 tons of CO2 per person in 2024. And where this CO2 is coming from are from all these different sectors here. So what we see on the left, this is just the same as on the right, except now they have this electric power right here, which is essentially the electric power that's needed to actually produce the electric power for all these different economic sectors here. So this one on the right is just showing it with this purple distributed into each one of these sectors right here. And so what we see is that the transportation, the residential and commercial, and the industry here are making up the lion's share of the greenhouse gas emissions. And when we look at these emissions over time, it looks like this. So what we see on here is in the black, this is the actual emissions each year. So that shows up on the right side. Then in blue on the left here, we have the actual atmospheric carbon dioxide, which is in parts per million. Where we can see over here on the right, the emissions are in gigatons. And so we can see that as the emissions increase, the amount of carbon dioxide in the atmosphere is also increasing. This, of course, is a correlation. We can't establish a causation here, but it's somewhat telling, and mixed together with everything else we're talking about, it makes a pretty good case that the carbon dioxide in the atmosphere is coming from human activity. And so why care about CO2 and other greenhouse gases are worse? So what we can see here in this graph is essentially how much stronger of a greenhouse gas each of these things are. So if we set carbon dioxide to 1 here, then methane is about 28 times stronger of a greenhouse gas compared to carbon dioxide. This HFC and this PFC here are just fluorinated hydrocarbons. We can see that those are both quite a bit stronger than carbon dioxide, as is nitrous oxide. Then this sulfur hexafluoride is extremely strong compared to the carbon dioxide. So why care about the CO2 and other greenhouse gases are worse? And one of the reasons for it is that human activity produces a lot more CO2 than other greenhouse gases. So we can see here these 3 different greenhouse gases, the carbon dioxide, the methane, the nitrous oxide. All 3 of these are increasing, but we see that the CO2 is in parts per million on here, where the nitrous oxide is parts per billion and the methane is in parts per billion. So these 2 are actually 3 orders of magnitude less than the carbon dioxide. So we're putting a lot more carbon dioxide into the atmosphere, and the carbon dioxide, we can see see from here is contributing a lot more of this radiative forcing than all of these other ones here. In fact, we can see on here in 2023, carbon dioxide is contributing more to the radiative forcing than all of the other gases here combined. And so that's one reason why we care about the carbon dioxide more than these other ones, even though the other ones are stronger molecule per molecule. And another reason is because CO2 lasts for hundreds, even thousands of years in the atmosphere. If we compare this to methane, methane only lasts about 12 years, or at least has a half-life of about 12 years in the atmosphere. And so what we can see here, if we pulse some CO2 into the atmosphere, so say we just release a bunch all instantaneously, then at year 0 we're at 100%, we can see it drops off pretty fast up to about year 20, then it starts slowing down. We're only down to about 40% of that initial pulse at 100 years into the future. So you pulse some CO2 into the atmosphere, 100 years later, 40% of that will remain. Then you can see at 1,000%, it's actually a little bit more than 20% will remain. Then as we go to 10,000, we can see that we're at maybe 15%. So even after 10,000 years, 15% of your initial CO2 pulse will still be in the atmosphere. But then you might be asking yourself, how do we know that the carbon dioxide in the atmosphere comes from fossil fuel emissions and not from some natural source or even some non-fossil fuel source from humans? And the reason we know is because we can analyze the isotope ratios in atmospheric carbon dioxide. The reason this works is when we are up high in the atmosphere, if we have nitrogen, which there is plenty of in our atmosphere, then these cosmic rays from the sun can hit a neutron. This will run into our nitrogen and turn it into carbon-14 plus a proton. This carbon-14 can then get incorporated into plants, which can then get incorporated into animals. When the animal dies, it gets buried in the ground. The carbon-14 can then decay, turning back into the nitrogen-14, and that carbon-14 ends up going away. And that happens in about 5,730 years. Why this is important is because when we have this carbon-14 in the air, that can then get taken up by plants and animals, which when they die, they can then rot, and that can go back out into the air. So for the carbon-14, there is a bit of an equilibrium here. But if something gets buried, such as something that gets turned into coal or oil, then all that carbon-14 is going to decay, because this 5,730 years is a fairly short half-life, at least on geological times. And so anything that's been down there for millions or hundreds of millions of years, pretty much all of the carbon-14 is going to get used up. And so all of the carbon dioxide that's found from fossil fuels is going to be depleted in carbon-14. So what we see here, the different kinds of carbon-containing material have different relative amounts of the light carbon-12 and heavy carbon-13. Both of these are stable, they do not decay, and so we will have different relative amounts of the light 12 and the heavy 13 and the radioactive carbon-14 in our sample. So plant matter tends to be enriched in carbon-12, and that's just because the enzymes that plants use to actually fix the carbon is going to prefer carbon-12 containing carbon dioxide over the carbon-13 containing carbon dioxide. And so plant matter tends to be enriched in carbon-12, so it has more of the light carbon than, say, the atmosphere does. So volcanic emissions are enriched in the carbon-13, which means that the non-biological and non-fossil fuel sources of carbon in the carbon dioxide will have the normal amount of carbon-13. Whereas, like I said, the plant material is going to be enriched in carbon-12. The ratio of carbon-13 to carbon-12 in the atmosphere and in the ocean are roughly the same. So that means that going between the atmosphere and the ocean, we're not going to get wildly different ratios of carbon-13 to carbon-12. Then since carbon-14 is radioactive, it decays predictably over time with a half-life of 5,730 years. So the young organic matter has more carbon-14 than older organic matter. That's because of this radioactive decay, which is going to cause the carbon-14 to go away. And fossil fuels have no measurable carbon-14. Remember, those have been underground for millions, hundreds of millions of years, so all of the carbon-14 will have decayed in the fossil fuels. Then, as carbon dioxide concentrations in the atmosphere have risen over the past century or more, the ratio of carbon-13 to 12 has fallen. Remember, plant matter has more of the 12 and 13, so a carbon carbon-13 and carbon-12 ratio going down means that there is more carbon-12 than carbon-13 being added to the atmosphere. And this means that the source of extra carbon dioxide must be enriched in the light carbon-12. That tells us that it's coming from some kind of plant source in this case. Meanwhile, the relative amount of carbon-14, the radioactive carbon, is declining. The record of carbon-14 in the atmosphere is complicated by nuclear bomb testing after 1950, which doubled the amount of radioactive carbon in the atmosphere. After the Nuclear Test Ban Treaty of 1963, the excess atmospheric carbon-14 began to decline as it dispersed into the oceans and the land biosphere. In the last 4 decades, however, the decline of carbon-14 has been noticeably faster than can be explained by continuing dispersal of the atomic bomb-related carbon-14. So in other words, this is essentially saying that we did have this uptick in carbon-14 in the atmosphere due to the atomic bomb testing, but since 1963, the amount of carbon-14 in the air has been dropping faster than can be explained by just the mixing and dispersal of this carbon-14 from the atomic bomb explosions into the atmosphere. This faster decline is driven by the addition to the atmosphere of huge amounts of carbon dioxide from a source with no carbon-14. So this is saying that that increased rate of carbon-14 depletion from the atmosphere could only happen not just from the dispersal and mixing of the atmosphere, but from adding more of this carbon-14 poor carbon dioxide into the atmosphere. So as this carbon dioxide enters the atmosphere, it dilutes the ratio of carbon-14 carbon dioxide to total carbon dioxide in the atmosphere. So again, this is just diluting the amount of carbon-14 in the air by adding all of this carbon-12 enriched carbon from the fossil fuels. Taken together then, we are looking for a source of carbon dioxide that comes from terrestrial plants. Remember, this is because they are depleted in the carbon-13 and is so old that any carbon-14 it once contained has decayed to non-detectable levels and is capable of creating a pulse of carbon dioxide that is larger and faster than anything that's occurred in the last million years. And only fossil fuels meet all of the criteria in this penultimate bullet point here. And so again, this is just showing that the extra carbon dioxide in the atmosphere is in fact coming from human activity, and in fact is coming from the human activity of burning fossil fuels. And scientists have termed what we've been talking about here the Suez effect. So this is the name of the effect given to the depletion of carbon-13 and carbon-14 in the atmosphere due to CO2 emissions. And what we've seen since the bomb testing has been called the bomb pulse. So this is the pulse in the air of carbon-14. So we see the increased carbon-14 levels, and then after the testing discontinues, we see that the carbon-14 levels decrease as we go down. And that is the Suez effect coming back into play again here. And so what we know from this isotope analysis are essentially these two things here. The first one is that the carbon-13, carbon-12 ratio of atmospheric carbon dioxide is decreasing due to being diluted by the carbon-12 enriched carbon dioxide coming into the atmosphere from fossil fuels. And we know this because ancient plants, just like modern plants, preferentially use the carbon-12 rather than carbon-13. And so all of the fossil fuels, which come from organic matter, are depleted in the carbon-13, which is the same as saying enriched in carbon-12. And so adding all that carbon dioxide into the air is going to deplete the amount of carbon-13 in the air. And the other thing we know is summed up in these 3 points here. The carbon-14 content of the atmosphere is diminishing too fast to be accounted for by the oceanic and photosynthetic capture of carbon dioxide from the atmosphere. And this is determined by comparing the carbon-14 measurements, so the things that people actually go out and measure, and they compare that with predictions using simulations of the carbon cycle, which we'll talk more about in video 3. So only an enormous increase in atmospheric carbon depleted in carbon-14 can explain this observed rapid dilution of the carbon-14 in the atmosphere. And only the enormous amount of carbon from fossil fuel emissions is a large enough influx of carbon depleted in carbon-14 to explain the observed rapid dilution of carbon-14 in the atmosphere. And so these two things taken together tell us that the carbon in the atmosphere is coming from the burning of fossil fossil fuels. And so what we've seen in the syllogism, we've firmly established P5 so far, I think. P7 has been established somewhat by looking at the graphs showing that the CO2 in the atmosphere is in fact increasing, which is indicative of the fact that there is no mechanism to actually quickly remove the excess CO2 from the atmosphere. So the fact that it's actually building up is telling us that there is no mechanism to actually remove it from the air. And these other two here, so P6 and P8, which we still have to establish, we'll talk more about P6 in video 3 and P8 in video 4. And so now we'll look at some of the history here. So using numerous paleoclimate proxies, so those would be things like tree rings and ice cores and forams and things like that, and in much more recent times, data gathered by scientists, climatologists construct the history of the Earth's climate. These histories show a clear correlation between carbon dioxide levels in the atmosphere and temperature. And levels of carbon dioxide in the atmosphere have been rising since the late 1700s, right at the time that the Industrial Revolution was taking off, and CO2 has been known to be a greenhouse gas since the mid-1800s. Then the global average temperatures since then have been increasing without any other known changes in Earth's energy balance. And so what we mean by this, we can see this is the levels of carbon dioxide for the last 800,000 years. We can see this follows a pretty regular cycle where the highest ever got was 300 parts per million, but now in the modern times we've shot up to 422.8 parts per million in 2024. And so we're pumping a lot of carbon dioxide into the atmosphere. And what we see is this warming trend right here, especially since about the late 1700s, early 1800s, we can see this trend in warming take off. And I have several graphs that look like this, but all of them have little things in it that I kind of like. So this one shows a few of these eruptions here, and what you can notice a lot of times with these eruptions is that right afterward we get a small dip in the average temperatures. So we can see this from this eruption right here, this from this eruption right here, this small dip from this eruption right here, this small dip from this eruption right here. And the reason for that is because these eruptions put a bunch of aerosols into the atmosphere, which actually reflect some of the sunlight back out into space. That causes a cooling effect. And so those would have a negative radiative forcing effect. Over here, once we get to the Industrial Revolution, we see that this temperature just shoots up and does not come back down. And so that is indicative of something much more long-lasting and permanent going on in the atmosphere. And then I have this graph, which is from much more recent times, but this is talking about something that we mentioned earlier, and we'll be talking about quite a bit more in the next video, which is the fact that the energy coming in, represented by this yellow graph here, is greater than the energy going out, represented by this purple graph here. And so we can see this is the difference right here in the energy coming in compared to the energy going out. And this one has this radiative forcing at about 0.86 watts per square meter. I've seen other ones that have it at about 0.76, but they are all in this ballpark right here. So we do have this radiative forcing. We are actually getting more energy coming in than we actually have going out. And we can see that this separation has been increasing over time. And that's because we keep putting more carbon dioxide into the atmosphere than what's leaving the atmosphere. So this right here is our radiative forcing. This next graph is somewhat straightforward. So we have with the black line here, this is the amount of carbon dioxide represented on the right axis right here. Then we have the temperatures here represented on the left side axis here. So this is the temperature anomaly. So this is telling us how much the temperature has changed compared to this 20th century average right here. And so again, what we see, the carbon dioxide increases and the temperature also increases, following right along with that carbon dioxide trend. And we can see this similarly in this right here. And what I like about this one that's a little bit different than the last one is it does have the sunspot activity, which tracks the sun cycle of slightly increasing and decreasing energy given off. And so one of the arguments I've heard skeptics of climate change make is that climate change is maybe just because of some activity with the sun, and this graph right here shows that it's definitely not that. The sun activity has been steady over the last 100 years, and in fact it's been been steady longer than that, but we can see that the warming is tracking the CO2 levels and not the sun activity. And so we can rule out the sun as the cause of global climate change. And then this graph here, which shows temperatures for both land here in red and in the ocean here in blue. And again, what we see is that both of these are warming. The land is warming faster than the ocean, which makes sense because water has a much higher heat capacity, but they are both in fact warming. And so this is not just some transfer of energy, say, out of the ocean into the atmosphere or some other explanation like that. Both of these things are warming. That's coming from the fact that more energy is coming into the earth than what's leaving it. And we can see that here. This is the temperature anomalies in 2024 all throughout the earth. We see, except for in a couple little spots right here, the temperature anomaly was quite high all throughout the planet. We notice that it is actually more in the northern hemisphere than the southern hemisphere. We'll talk more about that in future videos, but we can see that over the entire planet, the temperature anomaly of 2024 was in the positive, meaning that it was higher temperatures than was expected based on the reference temperature. This can also be seen when we look at a map like this, which shows us regions in 2024 that reached their either warmest or coldest day. And we can see that a lot of regions in 2024 reached their first, second, third, fourth, and fifth warmest days, but pretty much nowhere had its coldest day in 2024. And so that's another indication that the temperature is warming up over the entire planet, is that we keep having record-breaking warm days, but not cold days. And so we want to make some predictions about what's going to go on in the future. We'll talk a lot more about this in video 5, but just for a little preview here, climate models are computer programs that take in all the various atmospheric and oceanic data, run a bunch of computations, and output predictions. And the climate is a notoriously complex, dynamic, non-linear, recursive system, and so models have to be constantly refined and tested, and multiple simulations with slightly different initial conditions are run and then averaged together. And so I listed out these descriptions of the climate up here. So what I mean by each of them is, for complex, it means they have a lot of variables and they have multiple different interdependencies between the variables. Dynamic meaning always in flux. So a stable climate is in what's called homeostasis. So it's not in equilibrium, it's in homeostasis, which means that everything is in flux, but the fluxes are all at a relatively steady state, and so there is no net change, even though nothing going on is actually occurring at equilibrium. Then nonlinear just means that small causes can lead to enormous effects. This is also known as the sensitivity to initial conditions or the butterfly effect. Then recursive just means that there are lots of feedback loops. So when one variable changes, numerous other variables also change in response, which causes a change in the initial variable, and so you get a lot of this feedback going on in these systems. Then the other thing we have to remember about these predictions is that measurements, so the things that people actually go out into the world and measure, have limitations on precision. So we can't go infinite places past the decimal, for instance. And so while adding all the variables to our model may at first seem like a good idea, we have to remember that each new parameter added to the model will add new sources of error, which can accumulate fast during the course of simulation. And so that's why these simulations pretty much always have these error bars on them, and you can see that they get larger as you go into the future. So it looks something like this, where we can see right here, this is historical. They do run their simulations on these historical data, and that allows them to further refine their models so they can run their modeling on that historical data. Then we get up to the present time, and so now we see this is what's actually predicted here. And these are for different scenarios. We'll talk more about these different scenarios in video 5, but we can essentially see that this first one here in blue is essentially the scenario if we actually take some actions to help mitigate climate change, where this one here in red is if we essentially just continue with business as usual, which I think is the colloquial term for that one right there. And so we can see that if we actually take action, that we will still get some slight warming, because we are still committed to some warming based on the current positive radiative forcing, but we can see that then that will then slow down, it will come to a stop, and over the next few hundred years it will actually start going down. But if we continue with with the business as usual, we see that we end up getting quite a bit more warming right here. So this on the left is our temperature anomaly right here. We see that by 2300 we'd have about 7 degrees of increase in the temperature. But the other thing we can see is that as we go further and further into the future, these error bars get larger and larger. That's because, like I said, there is finite precision on our measurements, so we do have that slight error, which will keep getting bigger and bigger as you go further into the future. But that's what the error bars are for there. And these numbers here are telling us how many simulations they actually ran during that time. And this is just the amount of ice here on Earth in glaciers given these different situations. You'll notice these have SSP, where this one up here used RCP. Those are essentially the same thing. The RCP is a somewhat older version of this, so the SSP are the newer versions of these possible conditions, which, like I said, we'll talk more about each of those in video 5. But again, what we see here is that over time, the amount of ice in glaciers is going to fall, and it's going to decrease the most in our worst scenario here. So that's the SSP5 right there. We see that it's going to go down mostly in that, whereas with mitigating actions that this will fall, but then it will start evening out over the next 100 years or so. But we'll look at more predictions and how these models actually work in video 5. So in this video, what I just want to point out is that we have somewhat established all three of these right here. I think P5 is the one that is most established by this video, but P6 and P7 are also at least partially established in this video. But we will lend further support for those in the next few videos. Then P8 is going to be covered in video 4, so we'll talk about that quite a bit in video 4, and we will have established all 4 of these by the end of the last video. And so that's how we know that human activity is at least one of the causes of climate change. So what we're going to look at in this video series, so video 1 you just watched, but video 2 we will discuss the greenhouse effect and how it actually works. And it works slightly but importantly different from the sort of pop science description that usually talks about the Earth as a greenhouse. Then in video 3 we will discuss some of the things that complicate the sort of simplistic picture of pure energy balance that we will talk about in video 2. So in video 3 we will talk about things like the carbon cycle, the planetary cycles, various feedback loops, and a bunch of other stuff that can complicate that picture. But as we'll see in that video, it does still show that global climate change is happening and is actually likely to get worse in the future because of these various feedback loops. Then video 4, as I said, we'll discuss carbon dioxide and why it is a greenhouse gas. Then video 5, we will discuss how climate modeling works and what such models predict for the future. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.